Alrighty, guys. So let's go over polyprotic acids really quickly. So we talked about how when we have an acid, basically they release a proton, H plus, into the solution, right? That's pretty much the definition of an acid that we've been working with. Now, polyprotic acids are acids that have more than one ionizable proton. Basically, they can release more than one H plus. Okay. Okay, so polyprotic acids are a little bit interesting because unlike bases where, so for example, if we have, let me find my pen. When we have a strong base, for example, like BaOH2, we learned how this thing almost completely ionizes into Ba2 plus and two separate OH minuses. Do you guys remember that? Yes, okay, for sure. Just want to make sure. It's been a long week. Okay, so this is what happens with a strong base. Okay, but we learned how weak acids, they don't separate, they don't release all of them don't release their protons. Now, the interesting about polyprotic acids, so for example, here we have H2SO3, is that polyprotic acids don't release both hydrogens at the same time. That's kind of the key thing to keep in mind. Instead, they're going to release one hydrogen at a time. And so if you guys take a look, this acid is going to break down into H plus and the conjugate base right here. Okay, that makes sense? And it's going to have its own individual Ka. However, the conjugate base right here, if you notice, this is also an acid. This is a weak acid. So what it can do is this compound right here can have a second ionization where this guy releases an H plus. And that acid has its own Ka value. Okay, so it's like a two-step process, and each step has its own Ka or equilibrium constant value. Does that make sense? Okay, so if I draw another amazing picture of mine, so let's just say that we have let's do a generic acid. Let's say that we have H2 and then X for our anion. Okay, so this is our initial start phase. Okay, so when it dissociates, we're going to have HX minus and H plus in solution, right? Does that make sense? Now, you'll still have some H2X depending on the Ka value. We'll call that Ka1. And then the thing is, this compound right here has its own Ka value. We'll call that Ka2. Okay, so what this compound can do is it can release an H plus as well. And so we'll have all these different compounds inside of the same solution. And the ratio is going to depend on Ka1 and Ka2. That's pretty much what it's saying, okay? So each acid, even if it already released a hydrogen, has another Ka value to release another H plus, okay? So that's pretty much what you should have looked at the video from last time. The key thing to keep in mind is Ka2 is usually, most of the time, like 99.99% of the time, going to be a lot lower than K1, okay? So it's a lot harder to get rid of that second H plus, all right? Okay, that's a lot of info dump, but any questions? Okay. All right, so that's going to lead us into the first, I guess, big topic. It's going to be sulfuric acid. If you guys remember, this is one of the strong acids that you guys need to memorize. And so let's take a look at sulfuric acid because when the AP test talks about polyprotic acid, this is the one that's usually talked about, okay? Okay, so sulfuric acid is very interesting because it's a strong acid, right? So it's almost a complete ionization, okay? So it's going to break down almost completely into H plus and the conjugate base. Okay, now this conjugate base right here is a weak acid, and so this guy will not completely ionize. So it's going to have its own Ka value, okay? So just keep that in mind because they like to use this kind of to trick you, be like, hey, this is a strong acid. And then they set up the problem that you use so that you solve the problem where you think this is a strong acid as well. So just keep that in mind, okay? Sulfuric acid, the first ionization is going to be complete, but the second one will not be complete, okay? So just keep that in mind. If you want to jot that down somewhere, that might help. H2SO4, you might want to write that the first ionization is complete, okay? But the second ionization is going to be incomplete, okay? So just keep that in mind. And so what this means actually is that when you do problems with polyprotic acids, you're going to have to set up two ice tables. Okay, the first one is for the first ionization. The second one is for the second ionization. Okay, and I'll show you guys how that works in just a second. But any questions on the concept? Does it make sense? Alrighty, so let's do 12.35. And I will go through this step by step with you guys just so that we're all on the same page. And then we will move on to the next one where you guys can try this double ice table problem on your own. Okay. Okay. So it tells us that the solubility of CO2 in water at 25 degrees Celsius and 0.1 atm is this right here. So this is going to be the molarity. Okay. Okay, we're gonna assume that all the dissolved CO2 is in the form of carbonic acid. So we got our acid, which is produced in the reaction below. So we got our reaction right here, and we have the first Ka and we have the second Ka. Okay, so basically what this is telling us is that a lot of the stuff is kind of fluff information, basically just telling us that this in water produces that. Okay, so this is our first acid. Okay, so what we're going to do first is we're going to find the pH. And in order to find pH, if you guys remember, we need the H plus concentration, right? Okay, we're going to find the pH of this solution, and this is the molarity, okay? All right, so in order to find the H plus concentration at equilibrium, because this is going to dissociate and go into equilibrium, we have to write an equation. Okay, now our equation is not given to us. We need to write the acid dissociation reaction. So this is our acid, right? H2CO3. And we're going to write our equation. It's going to go into equilibrium because of weak acid with H plus and CO3. Oh, HCO3 minus. Okay, does that make sense? Why we write that equation? Yes.
The 3.037 molarity, is that for CO2 or for H2CO?
This one right here.
So it's like, okay.
Yeah, because all the dissolved CO2 is in the form of that, so it's going to equal.
Okay.
Yeah, so the wording is a little bit confusing here, so just be careful as you're going through it. Does that make sense though? Why? All right, so far so good, guys? Making sense? Okay. So the first part is pretty easy. It's just a regular ice table problem. So what we're going to do is we're going to set up our ice table. And I want you guys to take about maybe a minute or so, maybe about 2 minutes. I want you guys to try filling in this ice table, okay? See if you guys can find the initial values, the change, the equilibrium, and I want you guys to find the concentration, the equilibrium concentrations using the Ka right here. You can't see that very well. The first is -7. Okay, so take about 2 minutes. I want you guys to fill in the rest of this table. See if you guys can find the equilibrium concentrations of all three of your compounds. It'll take about 2 minutes to do that. Okay, guys, so hopefully you were able to identify that our initial concentration of carbonic acid is 0.0037. So we're going to plug that value in right here, 0.0037 molarity. And the reason why is because it tells us all of the CO2 is in carbonic acid, okay? Okay, so what values should we put for the products in this reaction? Yeah, 0. We don't start with any, right? Because we're starting with carbonic acid and then we're producing the products. So that means we're going to lose the reactant and we're going to gain the products. So for our equilibrium concentrations, at least for right now, will be 0.0037. We'll get X and we'll get X. Okay, so far so good? All right, now we don't know what X is yet, but we know the Ka value. And if you guys remember, Ka is equal to the concentration of the products at equilibrium divided by the concentration of the reactant at equilibrium, okay? Okay, so all we need to do is plug in the values right here. So we're going to plug in 4.3 times 10 to the -7 for Ka. Okay, for the top, we're going to do X squared because it's going to be X times X. And on the bottom, oops, I forgot to put this here. The bottom is going to be 0.0037 minus x. Okay, so far so good, guys? Okay, now, unfortunately, it looks like this is going to form a quadratic. However, one quick trick, I'll let you guys know that the 5% is going to work. 5% rule is going to work here. If the exponent is really, really small like this, if it's -7, then it's probably going to work. Good kind of ballpark number you can look at to assume the 5% rule works is something like -4, -5. At that point, you can kind of safely assume that the 5% rule will work. Not all the time, but most of the time. Okay, so if that's the case, then we can just do this. Okay, everybody good so far? Got it. Cool, cool, cool. Okay, so if we solve for x, you should get a value of about 4 times 10 to the -5. Okay. And so we can plug in those values right here. So this value is going to be about 4 times 10 to the -5. If you got decimals, that's totally fine, as long as you got something close to that. Okay, 4 times 10 to the -5. And then if you guys take a look at this, if you subtract this value from this value, it's not even going to change it very much. If you want to be a little technical, you could put 6. That works. Okay. All right. Any questions on that first dice table? That's good. Hopefully this is pretty easy now. Okay, so one quick thing I do want to tell you is that when you see a problem like this where you're trying to calculate H+, you'll be like, okay, I have the H+ concentration for the first ionization. I need to take into account the second ionization for H+ to find the pH. However, you don't need to do that. You can just find pH using this value. Okay, so what you can do is you can just plug it into the equation. pH is equal to the negative log of this value right here. Anyone want to take a educated guess on why we don't have to take into account the second ionization? Yes.
Because if we're taking away another hydrogen, it's still going to be the same.
No, because if this breaks down, you're going to release more hydrogens. Vivian, did you have a guess? No. Yeah.
It's like, to get base, it's gonna be like weak acid.
Mm-hmm.
So it's like most of the hydrogen is gonna stay in the acid. It's like reversible. Like it's gonna be such a small amount that it's not gonna change.
Yeah, is that what you're gonna say? Yeah. So yeah, that's exactly right. So if you guys take a look at HCO3 minus, again, this is a very weak base, and you can tell because look at how small the Ka2 value is. So even though some of it's gonna ionize, it's gonna release so little H+ into the solution. It's not gonna be much different than finding the pH value for this. If we did it experimentally, your pH meter would not even be able to read it, the difference. So we can just plug this in directly the way it is. Keep that in mind. It'll make your life a lot easier instead of trying to do the second one without figuring out the X value. So here we're going to find the pH, and it should be about 4.4. pH value is 4.4. Okay, so somewhat acidic. Make sense? Yes.
H2CO3. Oh, why did you write 0.0037 or an equivalent 0.0036 for?
Yeah, good question. So it's because you do minus X, and so technically this should be 0.0037 minus X. Now this value is really small, so if you punch in your calculator and got the same number, that's totally fine. I just put the 6 just to show mentally that it went down a little bit. Yeah, but either way works. It's a good question. All right, any other questions? You guys good? Okay, so that's how you find the pH for a polyprotic acid. Again, most of the time, you don't need to worry about that second ionization because it's not going to change the pH very much. Okay, so that's part A. Okay, for part B, it's asking us to find the concentration of CO3 2 minus. Now, if you guys take a look at CO3 2 minus, you should be able to identify that is the conjugate base of this compound right here, right? So you got a second ionization where HCO3 minus will go into equilibrium with H plus and CO3 2 minus. And so what the question is basically asking us to find is, hey, what's going to be the equilibrium concentration for CO3 2 minus? So this is where we'll set up our second ice table. And then basically the number that we get in this box right here. I'll put a happy face. Okay, this is gonna be the value that you're calculating for. Okay. Do you guys think you could try this one on your own, or should I go through it step by step? I should go through it. Okay, I will go through it. Okay, so let's go through this ice table. So we got to put in the initial values. Okay, so all we have to do is take a look at the previous ice table. Okay, what's the initial value for our product? For our reactant, sorry. Yeah, 4 times 10 to the negative 5. So 4 times 10 to the negative 5. Okay, we're also going to have an initial value for H plus as well, which is also going to be 4 times 10 to the negative 5. So far, so good? Okay, what's our initial value for CO3 2 minus? Yeah, 0, because we don't start with any of it. Okay, now here you might, yeah.
Sorry, why are we running an initial value of H plus?
Because we have an initial value right here for H plus.
Oh, it's great.
Yeah, it's the same compound, exactly. Yeah, so the first ionization releases some H plus, so you start with both of these. Okay, good question. All right, now since you have reactant and product, you might be like, hey, like, how's the change gonna work? Okay, but we have to keep in mind that this acid is dissociating. So are we gonna gain or lose more of this compound? Yeah, we're gonna lose. So this is the one that you're gonna get less of. If this guy breaks up, you're going to get a little bit more H plus, and obviously you're going to gain some CO3 2 minus. Okay. All right. So equilibrium concentration is going to be 10 times 10 to the negative 5 minus X for both of them. And so the point now is to just figure out what X is going to be. Okay. Yes. Minus X. Oh, sorry, plus X. Sorry. Yeah, I forgot to write that. Thank you. You're enjoying chemistry too much. Need to make this class worse. All right. So we got our values. So we're just going to be solving for X, and that will allow us to find our answer. So same thing. We're going to take Ka2 this time. So this was Ka1. Now we're solving for Ka2. Ka2 is going to be equal to 4 times 10 to the negative 5 plus X times X divided by 4 times 10 to the negative 5 minus X. And this is starting to look like a really, really, really ugly problem, right? Okay. Okay, and then we'll replace Ka2 with 5.6 times 10 to the negative 11. Now, we can use that trick I just told you about. If the Ka value is really, really small, if it's negative 10 to the 4 or smaller, we can assume the 5% rule works here. So here we can assume 5% rule works. So the change is going to be so small that it doesn't affect the concentration very much. Okay, so let me repeat that. Okay, we're going to use the 5% rule because the Ka value is so small for Ka2, which means that so little of this compound breaks up, you're going to make super little amount of this, and you're going to lose super little amount of that, so that the difference, the change, doesn't even matter. So we can basically say that none of it really changes. Okay? The only thing we need is X, because we still need a number to find, right? And so we keep that variable. And then from here, it's a super easy question. We just cancel out like terms. And so your X value is just going to equal the Ka value. So the answer is the concentration of CO3 2 minus is going to be the same as the Ka2 value. And that's it. Oh, so did you get to the part where I said the 5% rule and then you can get rid of it? Yeah. So if we do the 5% rule, right? At the top we had plus X and here we had minus X, right? So if we get rid of the plus X and the minus X, the change, if you notice, these two numbers are exactly the same, right? You got the same numbers on the top and bottom of a fraction. They just cancel out. So you get X equals 5.6 times 11. And that came from the Ka2 value right here.
Oh, I didn't see
Yeah, no, for sure. Yeah, please double check with me. It's a lot of numbers, a lot of exponents, gets really confusing. Yeah. Isn't this fun, guys? All this kind of comes together, and now there's 2 ice tables.
I love ice cream.
I should give you a triprotic acid.
That would be fun.
Whatever.
Is it actually a thing?
Yeah, H3PO4, phosphoric acid,
Will we ever have to do that?
probably.
You don't think
And
it's
the K2 value is so small, the K3 value is super insignificant. Yeah, it's basically 0. All right, but do you guys think you could try a polyprotic acid problem on your own? All right, let's try it out. We will move on to 12.36. Same thing as before. I'm gonna zoom in a lot into this problem just so you guys can see the numbers a little bit better. But again, this is gonna be on Canvas as well. So I'll give you guys about 7 minutes to try this out, and then I'm gonna start going over it. And then if you're still working on it, you can ignore me and finish it up and check your answers. But take about 7 minutes to try out this problem, and then we'll go over it in about 7 minutes. All right. Well, anyway, I know nobody's ever paying attention to me.
I pay attention.
I thank you. Thank you.
Like though?
I do. I just like talking to myself about chemistry. Okay. So the one thing I do want you guys to know is that here, if you guys take a look at the Ka1 value, what do you notice about it? It's big. Yeah, it's relatively very big. So hopefully you guys use your quadratic equation. If not, that's okay. But yeah, anyway, let's start going over it. I'm gonna kind of fly through it. So if you guys have any questions or I do something wrong, please just raise your hand and let me know. I already did something wrong?
No.
What's up?
If you have like a motor calculator that does like, can I use it?
Oh yeah, of course, yeah. As long before the test, I'll send you the calculator policy. Just make sure your calculator's on that list. Because if it's not, you could get in trouble for that. I don't know. I will send you guys a calculator thing. Sorry, I don't know what model calculators. There's like 200 on that list. Anyway. Okay. So first thing you want to do is write your equation. You got your compound, you got your acid, and it's going to dissociate first ionization, so it's going to be H plus and HC2O4 minus. Okay. So we're going to set up our ice table. Okay, we got our initial concentration for our acid, which is 0.02 molarity. We don't have anything for the others. So obviously we're going to lose some of the acid and gain the other 2 compounds. So you're going to get 0.02 minus X, X, and X. Okay, so for our Ka value, Ka1 is going to be 5.9 times 10 to the negative 2. Going crazy. Okay, top's going to be X squared divided by 0.02 minus X. So unfortunately, this is a quadratic. So hopefully you guys did your quadratic. I'm going to skip that part. It's going to be 0.0158 around there. They're asking a lot of me.
Please, Mr. Owen. Yes, please, Mr. Owen.
Why?
I got the wrong answer. Me too.
Okay. So you're going to multiply both sides by the denominator. Okay, I'm going to stop writing it with this. I'm just going to transcribe it. 0.059 times 0.02 minus X. Make sense so far? So all I did was convert this by moving the decimal 2 times to the flags. Okay. We're going to distribute. Man, you guys are making me do actual work.
You're a teacher.
I am? Oh, that's news to me. Who am I? What am I doing here? Okay, and then this is going to be the simplified version of that. Everybody good? Okay, we're gonna move everything to the same side. X squared plus 0.059 X minus 0.00118 is equal to 0, and you got your quadratic. Okay. All right, then we're going to use everybody's favorite equation. X equals negative b plus or minus the square of b squared minus 4ac all over 2a. Okay. If you're singing this outside of this class, I know. I've started a problem, dude.
Singing it to my mom in the car at like 5:30, and she was so mad. Like,
Dude.
and yeah.
Your mom's gonna think I'm like starting a cult here or something.
In this future, if you ever look around and wonder why things aren't where they are,
It's because of me. Because I've tainted the young generation, the future with that song. It's okay. Mr. Anderson taught me that in 8th grade or 7th grade. Sorry.
that explains why.
I mean, I
Yeah.
feel like we should.
Mr. Anderson broke me. Anyway, so this is how you plug it into the quadratic formula. So far, so good? Okay. All right, I'm gonna simplify directly on top of this because I don't want to write anymore. I'd rather just erase. 2 times 1. Huh?
You actually read it.
I'm gonna remember that comments as I grade your paper. Okay.
Oh.
Boom. All right. No, I'm impartial. Yeah, we can get rid of the ones because we multiply by 1. Okay. Let's simplify the 4 or the stuff inside. So 4 times 0.00118 is going to give us right here. Since it's a negative times a negative, it's gonna be a positive. So plus 0.00472. Okay. We're going to square 0.059. You're gonna get 0.00 about 35. And you're gonna add those two values up. Okay. Everybody good so far?
Yeah.
Am I going too fast? You guys need some time to copy it down? No? Okay. Good. Okay, so inside of the square root, you will get a value of 0.00822. Okay. And then we can find the square root of that value right there. And then that's going to give us 0.090, and I'm gonna round it up to 7. Okay. Okay, now from here, we already know which operation to use. Should we add or subtract? Yeah, we want to add because if we do negative minus, a number, it's going to become more negative. So the negative ones, the ones that we're not going to use, theoretically it's possible, but physically it's impossible. So we're going to use the addition. So 0.059. 7. And then for your numerator, you should get a value of 0.0317. And then if you divide that by 2, you're going to get the value that I mentioned earlier, 158 molar. You guys happy now?
Yes.
You guys happy?
Thank you.
Should delete the recording out of spite. Anyway. No, I'm just kidding. It'll be recorded, and then if you need to go through the steps for all the calculations, they'll all be on there. Okay. Okay. Let me. Anyone still copying this down? Okay. Let me. Yeah, I'll give you a second. You got it. Okay. All right. So I'm gonna erase it. If you need me to stop so you can take a picture or whatever, please let me know. Just don't take a picture of me like somebody here who I don't consent to. I don't consent. Okay, but it's not Allison. It's another person. There's another person whose name is a unit of measurement for distance. But I'm not gonna say any names. All right, so that's gonna be your molarity for H plus. So obviously pH is equal to the negative log of 0.0158, and your pH value should be 1.8. Everybody got that? Nobody's paying attention, huh? Oh, thank you. I appreciate you guys paying attention. All right, so okay, this makes sense though, because if you guys look at the Ka value here, ladies, okay, the pH value is, if you notice compared to the previous problem, it's a lower pH, right?
Yeah.
So it's more acidic, which makes sense because more of the acid is going to dissociate. It's a smaller Ka value, so more product, or bigger Ka value, so more of the product is made. So that makes sense. It checks out. Okay, so that's part A. All right, for part B now, what we're going to do is we're going to do the same thing. We're going to set up an ice table, but this time with the conjugate base, which is a weak acid. Kind of confusing. Okay, and this can be H plus and C2O4 2 minus, which is the concentration we're looking for. Going to set up another ice table. And we're going to bring our values down from the previous table. Okay, so for this right here, it's going to be this value right here, 0.0158. I'm gonna bring this down as well, 0.0158. 0. I'll lose some of this, gain some of that, gain some of this, and then there's so much writing. Kind of feel bad making you guys do all this now. I do. I feel horrible. Okay, so we got our Ka2 value. But if you notice, it's 10 to the negative 5. So again, we can safely assume that we can ignore the changes. So on the top, we're gonna get 0.0158 times x divided by 0.0158. And if you guys are noticing the pattern now, the concentration of your final conjugate base is usually just going to be your Ka2.
You're using like a stylus. The majority of the time, the answer just be Ka2 that we already knew. We just have to put that together.
It is, right?
I think it's the amount.
It is. It is. Yeah. So yeah, most of the time, there are some rarer exceptions where the concentration of the final conjugate base is not going to be Ka2, but most of the time it is going to be Ka2.
Well, on the AP test, the majority of the questions
I don't know.
probably like that.
I don't know. I wish I did. If I had the test with me, guys, I'd give it to you at the risk of perjury, or not perjury, but whatever that. I don't know legal terms.
Been using stylus?
Yes, since
Forever?
beginning of the year. I can't write, dude. If I write with the mouse, it looks like I have like a carpal tunnel or something. Look, like
Did you write with the mouse? I thought you were writing with the mouse. I was always really impressed.
oh, dude, it looks like I have a tremor or something. Jeez, look at that.
You should have said that in your
What?
your interview to like become a jury.
That I have a tremor?
Yeah.
I clearly don't have a tremor, right?
Just like start shaking.
All right, let's move on. You guys are strange. All right, actually, let's take our 5-minute break, go to the restroom, and then we will come back and continue with weak bases. All right, so we've been talking about acids. Now we're gonna come back and talk about bases. We talked about the strong bases that I recommend that you guys memorize. But just like how there are weak acids, there are also weak bases. And basically the same concept. Weak bases don't dissociate completely. Okay, it's pretty much the same concept as weak acids, just with bases now. Okay. Everything else kind of carries over too. There's going to be an equilibrium constant for the dissociation of bases. Ka is acids, so it's going to be Kb for bases. And it's going to be like this. Right? Making sense? Literally like the same thing, just with bases. Okay. So the difference here is that bases are either going to release OH minus, going to release me, or they're going to absorb an H plus. That's another way to think about it. Okay. So a lot of bases are going to release OH minus like this, but then examples like this NH3, it's going to steal an H plus from water, and that's how it acts as a base. So that's another way we can think about bases. So the equations can get a little bit more complicated, but the ways to think about it is, for example, if we have like LiOH, that's a strong one though. Guess we can think about water. Let's talk about water. So H2O is a strong or a weak base as well, because it can release OH minus, right? Or another way we can look at it is things like this, where NH3, it absorbs H plus and it produces two products. Okay. So the equations kind of get a little bit more complicated. So you can think about it as releasing OH minus or absorbing H plus. All right. Any questions? Got it? Yes.
Are you the first person to ever write water is HOH?
No.
He is the first person.
No, we do this all the time because it's kind of easier to see the H and the OH.
Okay.
Yeah. But yeah, I'll take credit for that. I invented chemistry. Yes. Yes, that's a good way to think about it. Yeah.
So like as opposed to like the acids.
Where you concentrate on H plus, yeah. What's up?
It's about.
Uh-huh.
Did you go there?
I got my master's there.
My
Oh, really? Good for them, him or her. Viola. It's in La Mirada. It's like East OC, South or Northeastern OC or Southeastern LA. Are you sure? Are you sure? Give me the core. What's the exact? Give me the exact distance. Give me the exact distance from here. Yeah, see you. So you don't know where it is. You don't know where it is. All right. So let's move on now. Yeah, I mean it's a Christian school.
Yeah, that's
It's a Christian school. All right, so let's go to disable. So take a look at it. So here we're gonna compare some weak bases. And same thing as before. I'm just I feel like I'm just reviewing because we are. The stronger the weak base, the higher the KB value, and the weaker the base, the smaller. Yeah, basically same thing. All right, so with that being said, let's move on to the fun part, the actual math part. So what we're gonna do is we're gonna calculate the concentration of OH minus for this solution right here. So I'm gonna help you guys out with this, and then that way we can move on. But it's very similar to what we've been doing. We got NH3 as our base. Now, this is going to be a little bit different from our acid because NH3 does not release OH minus by itself, right? Yes, it needs to receive an H plus. So here we have to write the full equation of what it reacts with. So NH3 reacts with water, right? Because it's in solution. And water is a liquid. So we're not going to be caring about the water in the equilibrium concentration or anything like that, but we just use it for the balance equation. Okay, and it's going to go into equilibrium. Since NH3 is a weak base, it's going to steal an H plus from the water. It's going to take it away, so it's NH4 plus. That's aqueous. And then it's going to produce OH minus. So technically, NH3 does produce OH minus in solution, but it's not producing it on its own. It's stealing an H plus from water to produce OH minus. Okay. Isn't this fun? Science. Yeah, I'm not a fan of bases either. Yeah, I like acid. You like acid?
Yes.
Yes.
Okay.
We can go to help group for you if it's a problem, Vivian. All right, so from here, we're gonna do our ice table. So if we take a look at our ice table, one thing you should be able to see very clearly is what's important about water.
It's a liquid.
Yes, it is a pure substance. It is the acid here, technically. Okay, she can't stop thinking about acid. Okay, but H2O.
Okay. Don't say that.
All right. Vivian's parents, you heard that, right? What your daughter said about acid. All right, anyway. Pure liquid, so we can ignore it in terms of the ice table and equilibrium. Okay, let's plug in our values. What's your initial concentration of ammonia? Yeah, 0.15. And then what about the products? 0. You don't want to. Because you don't. All right. So same thing as usual.
But can we try it?
No. You can do it at home, but don't blame me. I didn't teach you anything about that.
But if we want to get out of school early, we could try.
You might get out of some other things early too,
Hey, that's
like life. All right, so we got our ice table, and then from here, I'll give you guys about 2 minutes to finish up the calculations. I want you guys to calculate the concentration of OH minus using this ice table, and you got the KB value right there. KB, if you guys can't see, is -5. 10 to the -5. Take about, I don't know, what did I say, 2 minutes to try that out, and then we'll go over it together. All right, so I don't know, guys. I feel like we're doing the same calculations over and over again. So KB is equal to x squared divided by 0.15 minus x. But if you guys notice, yeah, it's very small. We can ignore the change. We can calculate the x value as 0.00164 molar, something around there.
and then you like, you like crumble it a bunch until it gets really soft, and then you make like a drum out of it, and you put it like this.
I'm not a very musical or artistic person. No, never. I know that that's a very specific question. No, never. All right, let's move on. Huh? 1.00164 or 0.00164. Okay, let's move on to the next question. The next one is not a calculations question. It's more of a if you get the content. So, oh my god. Sorry. I'm dead. Okay, so I want you guys to just take a look at the problem, see if you can solve it. All right. Anybody want to share their guess? Which one will produce the highest pH? It's a 0.05 molar solution. Yeah. First, tell me the chemical. Yeah. Methylamine? Yeah, methylamine. Okay, so yes, methylamine is correct. Why will methylamine produce the highest pH? Yes, but how do you know that? Yeah.
This is my educated guess.
Okay.
So it wouldn't pass the 5% rule.
Okay.
This is why I also picked it. So when it's higher, it would produce a much higher pH.
Yeah.
When it's lower.
Exactly. KB is higher, which means it's a stronger base, right? And if it's a stronger base, the pH number is higher because anything more than 7 is going to be a base. So bigger the number, the stronger the base. So yeah, that's correct. So the answer is methylamine, and it's because it has a higher KB. You can just literally say that.
Would it be fine if you put, would it pass 8 or 5%?
No, you don't want to say that. You want to refer to what's on here. Yeah. 5% rule is a term that we use as kind of for that strategy, but so you don't want to refer to that. So.
If we have that problem, we have to like write it out and explain it, or do we have to just like, can we just say methyl, whatever?
This, since it doesn't say explain, you can just say methylamine. Yeah. But the reason, if it said explain or justify, then you would give me that's good. Exactly. Good question. All right, let's keep going. All right, we'll end with this. It'll be very, very quick. Okay, there are a couple types of, or 2 types of weak bases. Shh. Okay, weak bases, there are 2 types. First category, okay, and you guys might want to jot this down or paraphrase it. First category of weak bases are neutral substances that have an atom with a non-bonding pair of electrons that can accept a proton. What does that even mean, right? Basically, it can accept an H+. That's the first type of base. Okay, it can accept an H+. Okay, now some tricks to seeing compounds like that. See it in the first bullet right here. They usually contain nitrogen somewhere, okay? And so one good example of this type of base, it's going to be the one that we were talking about, ammonia, NH3, right? And it has a nitrogen. Methylamine, the thing that we saw earlier, also has a nitrogen. So that would be another this type of base. And usually they're in the ammonia or amine type of group. Okay, you guys don't know what that is. That's okay. You guys don't need to remember that, but that's just a term. Yeah.
So would like be like the name of the category, or is it like a subcategory within like the broader, like, like they're neutral and they can accept?
Amine is a very general way of talking about these types of compounds. So there's a big category called organic compounds, and inorganic compounds, amines are a type of organic compound. It's actually not specific to just acids and bases. Yeah, so you don't really need to know that term, amine. Yeah. But I might make you memorize it to be, because I am a mean teacher. Damn. Okay. All right, still got it. Okay, so 12.39. I want you guys to take a look at this compound right here, hydroxylamine. And just based on what we just talked about, and you guys don't need to write this down, which atom, and we got the structure right here, the formula, which atom is going to accept the proton?
it's. Oh, and.
It'll be N, yeah. N will accept it because if, let's say, for example, O accepts the H. Okay, so here, this is going to be the N. Well, that's not a good color. Will black show better there? Yes. N, H, H, OH, okay? So let's think about this. If O accepts the H, right? If the H sticks right here, what does O have to do with the H to accept it? Not balance, not break off. It has to have a lone pair, and what does it have to do with the lone pair?
Has to share them.
It has to share them. But if it's electronegative, does O want to share the electron?
No.
No, since this guy's way more greedy, right? O's are very greedy. We don't want to share. And so O does not want to share the electrons with H. And so nitrogen is going to be the one that shares with H. And that's how it'll form your.
So NH3.
So it'll be NH3OH. That will be the conjugate acid, yeah.
So,
Yes.
do we ever like do a structure or anything to find where the lone pair is, if we always just go to the like nice?
Usually you can just put on the nitrogen and oxygen. Yeah.
But it's like this, right? Oh, can't accept.
Not that it can't, but N is more likely to accept the H. That's probably a better way to say it. And if you guys remember from what we just talked about, that's the first type. The first type are the ones where the nitrogen is the one that accepts the hydrogen. Okay.
Mr. O, you watch Soap Today a lot?
It's oh, I shouldn't have that in the recording. Put the last thing. Okay. Okay, so the second category of weak bases are the anions of weak acids. Okay, so if you guys remember, there's always conjugates, right? Okay, so a conjugate of a weak acid is going to be a weak base. Okay, and that's basically the second type. Okay, so once an acid gives up its H plus, the anion, the negative part that's kind of hanging out still, that is a weak base. That's the second type of weak base. Okay. All right, and we will end with that. We'll do 12.40 when I return next week.